Good morning, everyone. We're going to pick up this morning with the chapter 10 and 11 review problems. This is the second packet that I posted on some review problems. Excuse me. We'll then get into some chapter 12 content. Probably get through that mostly today, if not a little bit into Wednesday's lecture. And then the rest of Wednesday's lecture, we'll look at some review. This Wednesday's our last lecture. Next Monday's our final exam. It's in this room here, 8 a.m. So anyways, let's get into this review problem here. So we're considering gas samples of O2 and CO2. We have two different containers of the gases. The containers are at the same temperature. The first question is, which sample has the greater average kinetic energy? That's kind of a trick question. They have the same average kinetic energy. So they have equal average kinetic energies because they're at the same temperature. So temperature is a measure of average kinetic energy. As you increase temperature, you increase the kinetic energy. If you decrease the temperature, you decrease the kinetic energy. Because the kinetic energy is constant for the two gases, that's how we end up with a relationship to velocity. That's how we end up with the relationship that the heavier particle must have a lower velocity to make up for that increased mass. So when we look at our root mean square velocity, we can either think, well, the lighter gas is going to have the higher root mean square velocity, or you can look at the equation. I was just double checking the final exam info. You can go to Carmen, go to the module for the practice exams for the final, see the practice final information, or the real final exam information packet that you'll get. There's 4 equations from chapter 10 that you get. You get PIV NERT, PV is equal to nRT. You get the van der Waals equation, that big one, that P plus n squared A divided by V squared, V minus NB. You get that big equation where likely you would never use math in that equation. You would only kind of compare what the A and B constants mean, but at least you can look at the equation to make sure you realize that A is correcting intermolecular forces, B is correcting the size of molecules. You also get the RMS equation, this one here, that is 3RT divided by molar mass. And again, I think probably wouldn't just ask you to calculate a velocity, but at least with this equation here, you can see that as the molar mass increases, the VRMS, the root mean square velocity, is going to decrease. So the heavier particles move slower. And so the sample with the greater root mean square velocity will have to be the particle that has the lower velocity. So of course we want to choose the particle that has the lower molar mass, so it has the greater root mean square velocity. And so comparing O2 and CO2, obviously CO2 has a heavier mass, 44 grams per mole compared to 32 grams per mole. So the O2 has the greater root mean square velocity due to being the lighter particle. If we could make a change to these gases, what would increase their average velocities? Increasing the temperature would be a great thing to do, because if we increase temperature, we're going to increase the root mean square velocity. So the temperature increase directly related to the velocity. So this works. That's going to increase the average kinetic energy, which is going to increase the particle velocity as a result. So A works. Cutting the volume in half would increase the pressure, but increasing the pressure doesn't change the velocity of the particles. You're going to have particles hit the container walls more often, but not with a faster velocity, not with a greater force. So B is not going to work. And then if we put more gas into the container, what's that going to change? That might change the total kinetic energy, but not the average. The average is still going to be the same. The average velocity of the particles, the root mean square velocity of the particles will remain the same. So to change the velocity of the gas sample, we either got to change the temperature or change the nature of the gas, change the structure of the gas to have a different molar mass. So then if we mix the two gases in a container, so if we took the two gases, maybe connected with the valve, open the valve so the two gases can exchange and mix, and then we put a pinhole in the chamber or in the container, which gas diffuses faster? It's going to be the one with the higher root mean square velocity, and it's going to be the O2. So the O2, faster moving particle, is going to hit the container walls more often, more frequently. It's going to therefore escape the container faster than the CO2. Okay, let's move on to the next page here. So when we have a liquid sample of CH2F2 and it evaporates, So what's occurring during the evaporation? So the evaporation would be this compound here as a liquid. Evaporation is it just turning into a gas. And so we're just breaking the intermolecular forces in the liquid. We're not breaking any of the covalent bonds in the compound. So we start with a molecule of CH2F2 if I'm sketching a Lewis structure. I might want to do the Lewis structure just to get a sense, is it polar or nonpolar? I end up with this. If I count my valence count, I get 20 valence electrons. So I'm going to end up with a tetrahedral molecule. If I said, what's this bond angle here between the fluorines and the carbon? That bond angle is not 180. It might look 180 here, but that's because this isn't the true structure. That's not 180, it's 109.5 degrees. So the real structure is tetrahedral. I can put the fluorines and the hydrogens wherever I want, doesn't really matter. But the key is that this bond angle is definitely not 180, it's 109.5 degrees. And so because of that, hopefully that's a way that you can see we get a partial negative charge on one side of the molecule that we don't have match on the opposite side. If I had CF4, nonpolar molecule, but CH2F2, this is a polar molecule. So it being polar means it's going to have, of course, a dispersion force between two adjacent CH2F2 molecules. The liquid sample is going to have dispersion forces, and it's also going to have the dipole-dipole force. So in order to evaporate this liquid sample, we have to overcome the dispersion forces that are linking the molecules together and also the dipole-dipole forces. We're not breaking any of the covalent bonds. So we don't break covalent bonds in the molecule. We also wouldn't break any hydrogen bonds because this molecule doesn't hydrogen bond because we need fluorine to be bonded directly to hydrogen. So we need an H attached to fluorine. We have carbon attached to fluorine, so there's no H bonds. Remember, hydrogen bonding is an intermolecular force of attraction. It's not a covalent bond. The carbon-hydrogen covalent bond remains intact, and then there's no hydrogen bonds between adjacent molecules of CH2F2. So we have to overcome both the dispersion and the dipole-dipole force. But the key is to know if a molecule has dipole-dipole forces is to assess whether or not it's polar or not. So we have to know our rules for determining polarity. And so the basic idea would be, think about the 3D shape, and then if you have the same atom in every spot of a trigonal planar, tetrahedral, trigonal bipyramidal, octahedral, or even linear like CO2, those would be nonpolar. So I want the geometry to have all the domains be bonding, and then I want all the atoms to be exactly the same as each other. So I want all the atoms to be hydrogen or all the atoms to be fluorine. The CH bond is never very electronegative, so all of our hydrocarbons generally are nonpolar without too much consideration of the geometry. But our sample here has to overcome those two forces. Let's look at the next question. Looking at some data on vapor pressure. Actually gives us a vapor pressure numerically in a unit maybe we're not used to seeing, but it's megapascal. But let's not worry about the unit here because it's just telling us what that unit is. And then for the CH3Cl, that it's lower. So one of the key details here is just comparing the magnitude, is just seeing that the compound for CH3Cl is lower. And so then what explains that difference? If I'm looking at the two molecules structurally, they're both tetrahedral. They're both polar. The CH3F we might think is more polar because it has the more polar fluorine, but chlorine is also bigger. So chlorine atom is larger in size. So the CH3Cl is going to have a larger dispersion force just to having a greater molar mass. And so then another thought could be, well, how does vapor pressure relate to intermolecular force? Vapor pressure is that one property that goes inverse. So our vapor pressure, let me try to get rid of this lag and disconnect again. I don't know what it is that makes the screen lag so much sometimes. Must be the same problem the football team had. A little bit of lag. Okay. They're saving their energy for the final exam, for the playoff, right? That's what I'm thinking. So vapor pressure. So vapor pressure versus intermolecular forces goes inverse. So the stronger the intermolecular force, then the less likely the molecule is going to be lost into the gas phase. So you can think vapor pressure is related to like a liquid sample releasing molecules into the gas phase. But if the molecule has really strong intermolecular forces, it's not going to release the molecule into the gas phase. So we need weak intermolecular forces to have a high vapor pressure. If we have high intermolecular force, we have a low vapor pressure. So because we have a lower vapor pressure implies that we have a greater intermolecular force. So the intermolecular force in the CH3Cl is greater than the total intermolecular force in the CH3F, just by virtue of comparing their vapor pressures at the same temperature. And so that's just telling us we have a stronger force of attraction. Now, what explains it? Well, electronegativity doesn't really help because fluorine's more electronegative. We would expect that if electronegativity was the explanation, then that should have given CH3F the stronger force of attraction, and then it should have given the CH3F the lower vapor pressure, but it has the higher vapor pressure, so it has to have a weaker force. So the electronegativity doesn't help us explain that trend. What about the dispersion force? That's a good explanation because the dispersion force would be higher in the larger CH3Cl just by virtue of the molar mass being higher. Similar structures, so if you have a greater molar mass with basically the same geometry, you'd expect there to be a greater force of attraction. So this could be a good explanation. So this might be the best answer. The dipole-dipole force doesn't help because, again, the dipole-dipole force would make us think CH3F should have been lower, not higher in vapor pressure. So this doesn't help us with the explanation. The covalent bond strength has nothing to do with this, let alone we'd have to maybe go to the chart to even compare which one's higher, but the covalent bonds aren't being broken during the vaporization process, only the intermolecular force. So the properties of intermolecular bonding have nothing to do directly with covalent bond strengths. There's no hydrogen bonding present because CH3F doesn't form intermolecular hydrogen bonds because fluorine's not attached directly to the hydrogen, fluorine's attached to the carbon. Said it a bunch of times, but fluorine only forms one bond in stable molecules, so it's only going to form one compound that hydrogen bonds, it's HF. And so the only way you know you have fluorine in a hydrogen bonding molecule is if you have exactly the example HF. And even if you did, even if hydrogen bonding was the explanation, it would have made CH3F have the lower vapor pressure, not the higher vapor pressure. So we need weaker bonding in CH3F that can be explained by a weaker dispersion force. So dispersion forces increase, pretty well if you have a larger size molecule. So that's what we're seeing here is just a greater dispersion force in CH3Cl compared to CH3F. Okay, we'll move on to the next question. We're looking at surface tension. So which member in each pair of liquids has the greater surface tension? So surface tension, like most of the other trends, is directly proportional to intermolecular forces. So if you have stronger intermolecular forces, surface tension is how strong is the surface of the liquid. The stronger the attractive force, the stronger the surface tension. Another way to think of surface tension is the energy you have to apply to a surface of a liquid to break the surface, to physically break the surface of the liquid. So the weaker the force, the lower the energy. The greater the force of attraction, the greater the energy you have to apply to break the surface of that liquid. And so when we introduce this branching point here, so CH3, 3C, CH2, that's just meant to imply you have a branched structure. And then this is linear, so this example here is straight chain. So linear is better than branched in terms of intermolecular forces. It's better to have a lot of atoms connected along together, and then you get the attractive force, the easier ability to get a strong intermolecular force. A branched structure leads to there being more cylindrical forces of attraction, and they just can't get as close together as each other, and they have a weaker ability to form intermolecular forces. So our linear compounds always have a stronger intermolecular force in their branched isomers. So compounds of the same formula, just double checking CH3C, that's 3, 4, 5, 6 carbons. So we're comparing basically the same formula. So these are both isomers of hexane, so they have the exact same formula as each other. If we counted the hydrogens in each, it's 6, 7, 8, I can't count, 9, 10, 11, 14. So this is C6H14. And then this compound here, same thing. 8 from the CH2, CH3 is in the middle. This is also a C6H14. Just making sure we see that they're isomeric structures. So having the straighter chain is better than having the branch chain. In terms of stronger forces, when comparing CH2Br2 versus CH3Br, having the second bromine gives a lot more dispersion force. So we're comparing a lot more dispersion forces, stronger attractive force in the CH2Br. So that's going to win out just by dispersion force, kind of like the previous examples. Having the second bromine gives a lot greater dispersion force. That's an extra 80 grams per mole, so that's good. for that molecule. And so far we have the linear and then the straight chain. Now, what about temperature? How does temperature affect intermolecular forces? Well, temperature is a measure of kinetic energy. Kinetic energy gives the molecules energy to break those intermolecular forces. As temperature goes up, more of the molecules are going to be in the gas phase, or vapor pressure has gone up. So temperature, if we remember from vapor pressure, we get that relationship where vapor pressure increases with temperature. And that's because we're giving molecules more energy to overcome the attractive force. So we're going to have more molecules breaking the surface. It's going to be easier to break the water surface at the higher temperature because we've already weakened we've given the molecules more energy. So it's easier to break the attractive force that's already been partially broken. We have more molecules in the gas phase as a result. So weaker bonding as we get closer to the boiling point of a liquid. We know if you had said, well, what about water at 125 degrees C? Well, water has such a weak surface tension at 125 degrees C, it can't even hold itself together as a liquid. So you can think, well, that's pretty bad. At 100 degrees C, you're breaking the surface of the liquid just by virtue of being at the temperature because the sample's boiling. So as we approach the boiling point, you're breaking the surface of the liquid naturally without even having to apply an external force. So we're going to have the straight chain, CH2Br2, water at the higher temperature. So we have a phase diagram question. Some of these questions I've taken from chemistry Olympiad exams. Some high schools take these as like a competition. Anybody in the room happen to take any of these tests in high school ever? Does anybody recall? A few people may at their high school maybe have like a chemistry Olympiad day or something. But some of these questions I've taken online from those exams. But anyways, a portion of the phase diagram is shown for some molecule here. And so let's see which statement is correct. So the sample sublimes at atmospheric pressure. That means standard atmospheric pressure of 1 atmosphere. So what happens at standard atmospheric pressure is if we change the temperature, we're just imagining going left to right here, changing the temperature, and then the sample would sublime under those conditions. So at 1 atmosphere, the sample would undergo and we have to know that this would be the solid phase, this would be the liquid phase, this would be the gas phase, so that would be a direct solid to gas transition, and that is what sublimation is. So statement 1 looks to be correct. If we look at a temperature of 80 degrees C and 1.5 atmospheres, which would be right about here in the graph. So we're just looking about 80 and about 1.5, somewhere around this region here. Is like, what phase does that represent? Is that solid, liquid, gas? If it happens to be right on the line, then it would be the equilibrium between two different phases. But we're pretty solidly in the gas phase. And so it says at this temperature and pressure, only the gas is present. And that is correct too. So we'd only have the gas present underneath those conditions. So we're just reading the graph, trying to see where would the point be in the diagram. If we said, what about like 60 degrees and like 3 atmospheres, then that would be pretty clearly on the liquid side. If we said, what about 10 degrees and 1 atmosphere, that'd be pretty solid, a solid at that temperature. So it's just about reading temperature versus pressure on the graph and trying to see what phase that corresponds to. And then if you happen to land right on the line, then that would be a liquid gas present at equilibrium. So we have the 2 phases present. If you happen to land right here, that would be the triple point. That would be all 3 phases would be present at equilibrium. So if we said, well, what phases are present precisely at this point here, you'd say all 3. Okay, so both A and B are correct here, or both statements 1 and 2 are correct. I think this is the last page of questions. My screen is freezing up again because it's blurry. It's not blurry on my end. This is, okay, there we go. Given the phase diagram below, which statement is false? So we're looking for the false statement. So the solid has a higher density than the liquid. And so this is the liquid phase, solid phase, gas phase. If the solid were more dense, then if I took the liquid and condense the liquid, I should be able to get the solid if it's more dense. But every time I condense the liquid, I just take a liquid and then go vertically straight up. That's applying a pressure to the liquid. If I compress the liquid molecules to be closer together, they stay liquid. In fact, if I take the solid and compress the solid, it turns into a liquid. And so that would show that the liquid is more dense than the solid. So the solid doesn't have the higher density here, the liquid does. So it looks like statement A is already our false statement right off the bat. We can make sure that the other statements are hopefully true, so therefore not the right answer to the question. Sublimation and deposition are the only phase changes possible at temperatures below point B. That's the idea of the triple point. So if you go below this point here, then the only phase transitions that are possible are between the solid and the gas. So we can only get sublimation, deposition. Deposition is the opposite of sublimation. It's gas to solid. And so that's true. And that's the meaning of the triple point. So if you go below the triple point, the only phase changes are solid to gas, gas to solid. No phase change occurs when the liquid phase is compressed at constant temperature. That seems to be true. So if I take the liquid phase, any of these liquid phase temperatures here, and compress and go upward, I stay a liquid. So under none of those circumstances would the phase change into gas or solid. So that looks to be true. When heated at 1 atmosphere, the substance will first melt. So if we take at 1 atmosphere a solid, it eventually melts and eventually turns into a gas. So we undergo the normal phase transitions of solid to liquid to gas at atmospheric pressure. And then this could possibly be water, because water has all these properties. Water has the property that its liquid is more dense than the solid, so the solid floats on the liquid water, and then has a normal solid liquid melting process. So this could possibly be the phase diagram for water. Okay, I think that's the last question of review for today, or for this point. So let's get into some chapter 12 content. Let me redo my screen again. It's got to be Wi-Fi. Okay. So chapter 12 is on solids and modern materials. We're going to talk just briefly about a couple different classifications of solids and go over a couple slides, talk very briefly about a few materials. And so really we're just going to focus on the classifications of solids and some of their basic properties here within this chapter. And we're not going to go over in too much detail the remainder of the chapter. So we're going to talk about how we classify solids based on the nature of the bonding between the solid. So we're going to look at some of the key categories of solids. We know a few of them already, like molecular solids, or like things like water as a solid has intermolecular forces. We know sodium chloride has ionic bonds. We know metals have some type of metallic bonds. So we'll talk a little bit more detail, slightly more detail about metallic bonds than we have so far. Then we'll talk about one other type of bonding that maybe we haven't talked about too much. That's the bonding in things like diamond, graphite. They have an interesting type of bonding that we'll discuss. So we'll try to look at a solid, try to think about what we know about the compound or the element or whatever the thing is, and try to base then an idea of what type of bonding would it have, and then what do we know about the bonding nature based on that bonding type, so we can describe the differences between different types of bonding. And then we'll also look at crystalline versus amorphous solids very briefly to get a sense of, what's the difference between something that's crystalline in nature, what does that mean, versus something that's amorphous. So we'll take a look at what those two terms and what they mean in this chapter here. And then we'll briefly talk about a few other details about metals and some of the bonding of metals and some ionic solids. So let's start with the compounds that kind of come right from the last chapter. If you take any of the liquids that have intermolecular forces or molecular liquids like water, CO2, et cetera, and then you further decrease their temperature, eventually they solidify. And so when they solidify, the molecules would still be held together by intermolecular forces. And so this could be things like, water, solid would have this type of bonding, all different, like any of the molecules from chapter 11 that we were talking about as a solid would have the same intermolecular forces as the solid. And as a result of having the weaker force of attraction compared to ionic bonds have stronger attractive forces, covalent bonds have stronger forces of attraction, these molecules are going to have lower melting points and boiling points because they have that weaker force of attraction. So this is the main kind of property you get with these substances, is that they don't have particularly high melting points or boiling points because of the weaker intermolecular forces. They don't have any insulating or conductive properties. You're not going to get solids like water to conduct electricity like a wire would within the case of something like a copper wire, behaving much differently than a solid. They're going to have a softer structure. You're not going to make a building out of maybe an igloo. I was thinking, I guess you can make an igloo out of ice, but that's going to be about it. You're not going to build a structure you hope to have integrity out of molecular compounds because of this weaker bonding. And so just showing a few hydrogen bromide, so HBr, large but not hydrogen bonding, so relatively low melting point and boiling point, still a gas at room temperature. You can think relative to 25 degrees C. What's the phase here? The phase would be a gas. If you take acetonitrile, boiling point above room temperature, melting point below room temperature, so this would be a liquid at room temperature. Acetonitrile, CH3CN polar, so it has the dipole-dipole force on top of dispersion force. Same thing with HBr, has a dipole-dipole force, but it's just such a small molecule in terms of its size. Having 2 atoms, not very good. Having more atoms is better. So we see acetonitrile has a boiling point above room temperature. I2, 2 big atoms, much bigger than bromine. So if you compare the atomic weight of bromine to iodine, 79.9 versus 127 grams per mole, 2 of them. I2 has a melting point and boiling point above room temperature, so we have a solid at room temperature. And then something like sucrose has a lot of hydrogen bonds. We saw sugars generally have a lot of OH groups in them, so they have hydrogen bonding. They have high melting points, so we have a strong attractive force, but just because we have a big molecule, a lot of dispersion forces on top of a lot of hydrogen bonding forces of attraction. So you can have variable properties in terms of melting point and boiling points, but still, again, you're not going to build a building out of sugar. It's not strong enough. You have a softer structure here. So let's take a look at some other categories. Ionic solids are another good category that we have a pretty good idea of a lot of the categories here of what it means to be ionic. So this could be, sodium plus, chlorine minus, so maybe chloride, sodium plus, ion, alternating in sort of shape. You can imagine any of the other ionic compounds having this basic solid structure. Now, these compounds have high melting points and boiling points because of the attractive force. You have the strong electrostatic force of attraction. It's like our molecular compounds don't have those built-in charges, or if they do, because they're polar, it's just not a very big attractive force, and so a much higher force between the ions in an ionic compound. So we get, therefore, high melting points and boiling points as a result. +1, -1 lithium fluoride, melting point over 800 degrees C. If you make the ions bigger, remember how we said that reduced the lattice energy? So if you're looking at lattice energy, the lattice energy of lithium fluoride was bigger than sodium chloride because the ions were smaller. Well, making the ions smaller lowers the lattice energy. So from chapter 8, we know that the lattice energy of lithium fluoride is greater than sodium chloride, and we see that the melting point trend follows the same trend, that lithium fluoride's melting point is greater than sodium chloride's. So weakening the lattice energy by increasing the size of the ions lowers the lattice energy, also lowers the melting point. But we can also then adjust the charges. If we go to strontium oxide, we quadruple the charge magnitudes. We greatly increase the lattice energy. We also increase the melting point. So strontium oxide has the greater lattice energy. So if we're comparing our lattice energy of strontium oxide to lithium fluoride, we recall that the 2 + 2- has the greater charges, therefore the greater lattice energy, and then it also has the greater melting point. So it also has the higher melting point as a result of that increased strength of attraction. And if we go a +2 with a +2 ion and a -1, then we're somewhere in between. We're somewhere in between with the lattice energy because we now have +1 with a +2 with a -1, so we've reduced the ionic attraction due to changing the charge of one of the ions back to being smaller, and then we kind of put the melting point in the middle. So we're just seeing the melting point trends kind of continue along and trend with the lattice energies. Now, one of the properties of ionic solids that you may not expect, that you may be surprised to see, that they're electrical insulators. Now, what that means is that the ionic solid itself doesn't really conduct electricity really well. Now, you can turn an ionic solid into a good conductor by dissolving it in water. So you take the ionic solid into water, and if it's water soluble, so if you take a water soluble ionic solid, using solubility rules from chapter 4, dissolve it in water, get a water solution, then the solution becomes conductive. So if you take an ionic solid that dissolves in water, you greatly increase the conductivity of water. You make an electrolytic solution. This is all from chapter 4. So just making sure that you see there's a difference between the substance behaving like a conductor when it dissolves in water versus when it's the solid, in its solid form, it doesn't have the conductive properties. It's actually more of an insulator, meaning it just does not, if you put a charge on sodium chloride on one end, it doesn't conduct that charge to the other end. But it's okay, these structures are brittle. You weren't gonna make a wire out of sodium chloride anyways because it's too brittle. So if you're trying to think of something we can stretch into a wire, it's not going to be sodium chloride, because if you try to hit this thing with a hammer, imagine you strike this with a force, what's it going to do? It's just gonna shatter. So you probably had a sodium chloride crystal, could be rock salt outside that you gotta break apart and break it into smaller pieces. That's because salts, if you just hit them with force, they'll break in half and you get two different halves of your crystal very easily. And then they almost like become brittle as a result. So brittle solids, not conductive of electricity, but they're extended networks of atoms held together by that ionic bond, and the ionic bond is electrostatic forces of attraction. It's that kappa Q1, Q2 divided by D, so it's the electrostatic forces of attraction that are holding these ionic solids together. Okay, so hopefully we have well, I think we came in probably with a pretty good understanding that that's what ionic solids would look like, but a few new properties here: electrical insulators, and they're brittle. Let's talk about covalent network solids. This is the category we haven't talked about too much, though we encounter a fair bit. These are the structures in things like diamond. So diamond has this structure, graphite. Those are two different allotropes of carbon. So carbon is more stable as graphite, slightly less stable as diamond, but diamond is stable enough you can find it. So what diamond is it's a three-dimensional array of carbon atoms. So it's carbon linked together in 3 dimensions of tetrahedral carbons. I don't necessarily want to go too far with this, but if you imagine a tetrahedral with a carbon at every spot, it just then continues with a tetrahedron at every single spot. So you then just continue to have carbons at every particular spot, and so you can then just continue every single carbon in all 3 dimensions with this tetrahedral group, and that's how you get the base structure of what a diamond looks like. So you get a strong force of attraction. Well, like the covalent bond, it's about half the strength of a typical ionic bond, but you get 4 covalent bonds per carbon. So even though any one covalent bond is not particularly strong compared to the ionic bond, it's like half as strong, you get 4 of them per carbon. So you're getting a tremendous strength due to having all of these covalent bonds. And then you get a different property. Imagine I hit this with a hammer. Those bonds are going to hold up. So those bonds are going to generally hold up, and we're not going to be able to easily break the structure. So we get a very hard structure that's going to be hard to break, but if we hit it hard enough, it eventually will shatter. So if we hit this thing hard enough, it can actually break into pieces still. So again, probably not going to like have most of these items be the building blocks of our buildings because they're too brittle. They're not going to hold up to a strong force, but they're hard enough that they can hold up to some force. So hard structure, you can cut things with a diamond. So a lot of saw blades have diamond tips in them. Most of those diamond tips are man-made diamonds instead of the more precious natural diamonds. You get a lot of electrical properties. You can have some types of covalent network compounds be insulators, but a lot of times they're semiconducting, and this is good for computing. You see like silicon used in chips, gallium phosphide a lot as well. So these properties, semiconducting, think of it as conductivity you can turn on and off. So if you want something to be conductive some of the time based on the voltage you apply a small voltage, maybe it's a non-conductor, apply a little bit more of a voltage, it turns on. And so that's the idea of semiconductors, is they have a conductivity that can be shifted on and off. You'll see metals have such a high conductivity, you're never effectively turning it off. So metals are good conductors that can't be turned off effectively. Semiconductors can have the variable properties of being conductors or non-conductors. So what other things? Oh, one other thing you can say, high melting points and boiling points due to the collective nature of all those covalent bonds. So having the tremendous number of covalent bonds linking all the atoms together gives these properties a really strong structure that has a high melting point and boiling point. Diamond and graphite are over 2,000 degrees C, so really, really high melting points. Silicon over 1,400 degrees C melting points. Germanium, germanium's in the same group, carbon, silicon, germanium. So those are kind of forming your key kind of groups. Notice the germanium's dropping. Carbon, diamond was around 2,000 degrees C. So really high melting point for diamond. and for the things in the row of carbon on the periodic table. Gallium phosphide, we're not going to get too much into maybe identifying or predicting if the structure is or isn't a semiconductor, but the thing that's kind of interesting with, if you take usually the elements that are silicon go 1 over on each side, so like aluminum phosphide, gallium arsenide. If you have like a 3 plus and a 5, if you add up to 8, usually you end up at a semiconductor with your metalloid elements. So gallium phosphide, semiconductor, high melting point. And then silicon dioxide maybe is one you wouldn't have predicted because it looks like CO2. You would think SiO2 and CO2 would share a lot of properties, but they actually have very different properties. SiO2 forms a covalent network where it has a network. We'll see a picture of SiO2 a little bit later in the slides. But SiO2 forms a 3D array of covalent bonds, giving it a high melting point. And then SiO2 is actually what you have in glass and quartz. So you can think glass and quartz, those generally have higher melting points than carbon dioxide does. So you have something drastically different going on in SiO2 than you do in CO2. Now, polymers, you probably won't see polymers like on the test or anything, but I just wanted to briefly mention that polymers are having a particular repeating group that repeats itself millions of times in the structure. And so you could have something like CH2 be the repeating group. So imagine you have a structure that has this particular group here that just repeats up to, like thousands to millions of times. So you have this repeating group, and then you have a carbon chain that's like 1,000 to 1,000,000 carbon atoms long. And so that's what we call polyethylene. And so polyethylene is, I believe, what's in like saran wrap. So polyethylene, just a very basic plastic. So you get a lot of types of plastics that are polymers. Most of these are some type of plastic. I doubt anybody, has anybody ever seen the movie The Graduate? It's from like 1968. Has anybody ever seen this movie? It's a classic movie. It's one that's interesting, but there's this line in the movie where this kid's graduating college. I actually think he's graduating high school, I believe, but one of the two. And some guy comes up to him at his graduation party and says, look, one word, plastics. It just keeps saying plastics, like that's the thing he had to go into for his career. And so plastics or polymers, you can study, there's all different kinds of ways of coming up with different polymers when you change the repeating group. If you put a chlorine in place of one of these hydrogens, then you strengthen the structure. Then you have polyvinyl chloride, PVC. Polyvinyl chloride is that strong plastic that's like in the dashboard of cars. So it's a harder plastic than saran wrap. Polystyrene. Does anybody know polystyrene, where that comes up in nature? That's styrofoam. So this is the key kind of property in styrofoam. Car tires have vulcanized sulfur-linked cross chains of the neopenyl group, the C5H8 group. So like rubbers have this particular repeating group. So you just have long chains of atoms held together where the cross chains are linked by some type of covalent bonding force, if you have polystyrene, the molecules have the intermolecular force of attraction. So adjacent strands of the polymers have intermolecular forces linking them together, but these being such a long strand, they have a really strong attractive intermolecular force due to their increased size. And then you have a ton of mechanical properties that can be, based on the particular repeating group. So you can change the repeating groups, come up with all different types of properties, generally electrically insulating. These are going to be, because they're flexible, what you tend to wrap a wire in. So you wrap a wire in a polymeric plastic so that you separate the wires in an electrical situation from each other. And then they have intermediate melting point and boiling points. You can change the boiling points depending on the nature of the atoms, but usually you think relatively high, but eventually they usually melt and degrade. So if you heat up a polymer, usually it's going to like catch on fire or melt or degrade if it gets too hot. So a lot of different properties for polymers. Metals. So metals are extended networks of atoms held together by metallic bonding. So this would be things like iron solid, Fe solid, sodium solid. So it's the force of attraction between metallic elements. We're going to get a strong force of attraction here, and it can depend on the metal. We know mercury is a metal that's a liquid at room temperature, so it's not always super duper strong. But some metals are going to have really high melting points, some low melting points. Now, metals are generally said to be malleable and ductile. So malleable means that they can be pounded into sheets. So you can make like sheet metals, and then ductile is this stretching into wires. So you can make metals and sheets out of most metals. Most metals are good conductors of heat and electricity, so they have lower specific heats than metallic solid, than the non-metallic solids. So like water, higher specific heat than like iron, aluminum, low specific heats. So easy to heat up. And then also they conduct electricity really well. That's why we might stretch these into wires, is because you have a wire of copper, the Jesse line. What's the best element to conduct the electricity, Jesse, from Breaking Bad? You guys remember the scene? Who's seen Breaking Bad? And what does Jesse say? Remember, he goes, oh, wire. And Walt's trying to get him to say copper. And he's like, copper. But yes, so we make our wires out of copper and metals because they conduct electricity really well. And so to be a good conductor of electricity means I should be able to like add an electron here. If I put an electron near the metal, all the electrons flow towards the metal. So we'll need to come up with a model of how that works. So we'll talk about a model in a moment on how metals can act as good conductors of electricity, but they tend to have high melting points and boiling points in general compared to their neighbors on the periodic table. So usually, metals, high melting points, that's why those are solids. Right side elements, gases, weaker intermolecular forces. Few melting points to compare: magnesium, high melting point 650 degrees C, silver, almost 1,000, titanium, 1,600 degrees C, tungsten, and old light bulb filaments, over 3,000 degrees C. So really high melting points. So one of the models of metals that kind of shows perhaps why they can be malleable and ductile, and then also how they can conduct electricity. If we picture something like iron, I like using iron as a good example here because we can think sheet metal. You can think copper too. Copper's not a bad example to think here too, because copper we tend to think of it again as in wires. And so both these metals have a lot of valence electrons. So if you put two iron atoms next to each other, or a bunch of iron atoms near each other, they're all kind of sharing in those valence electrons. Same thing with copper. So you imagine a metal that has way more than what we're showing here. Imagine a metal that has 6, 7, 8, 9, 10, 11 valence electrons around each of the metals. So each of the metal nuclei is almost surrounded by what we call a sea of electrons. So it's almost like each metal has almost like a liquid sea of electrons that is fluid, in a sense that if we add an extra one, the electrons flow away from it. If we remove an electron, if we kick one of these electrons out, then the electrons are kind of like a liquid. They will flow towards that electron very quickly to replace it. And so you get a fast conductance due to just the idea that the metals are just surrounded by electrons because of their high valence electron count. And so another thing that you can imagine is if I start moving these nuclei, because I'm like pounding with a hammer, if I start moving the nuclei, the electrons just kind of go with them. So the electrons just kind of go like a fluid and kind of fill in wherever the metal nuclei happen to change spots to. So we start rearranging the shape, we compound this into a sheet, stretch it into a wire, and then the electrons just kind of follow along and go for the ride. And so that's the sea of electron model that can help us explain some of the properties of metals. This slide here is going to show us that if you're picturing metals kind of from like an MO perspective, what ends up happening with most metals is, you start with maybe one valence electron, you have another electron here, and then they go into like a bonding MO. This looks kind of like hydrogen. And so if you imagine like two hydrogens next to each other, now hydrogen's not metallic, but maybe we imagine two lithiums next to each other, like two Li2s next to each other, and then these, so if I picture this next to this, then we go up and down. And if I do it again, if I take this structure and put it next to that structure, gone back to having the delay here. So again, just picturing these two configurations next to each other, and then they would split each other. And so what you end up with metals is you end up with a tremendous number of filled molecular orbitals that have electrons in them that have a variety of energy. So you have like a huge like series of states that are filled with electrons, and then you have all the unfilled orbitals that are accessible that have no electrons in them. So the empty MOs are like right above the filled MOs. So it's like if you had an orbital with electrons that are very high in energy, and then right above it you had an unfilled orbital, I could put the electron into the unfilled orbital, and that's a way that the electron can then conduct through the metal. And so a way of explaining the conductance of metals is there's no real energy associated with moving the electron from one orbital to a higher energy orbital. And so that's another model for conductance, is if you had a structure, like imagine nitrogen. Remember the MO diagram of nitrogen has all of the MOs filled. We end up with a bond order of 3. And then we have all the antibonding orbitals up here. Well, N2 is not electrically conductive because it takes a lot of energy to promote the electrons from its occupied orbitals to its unoccupied orbitals. Let me change my screen again. This delay and lag is gonna be the end of me today. Okay, so if we're picturing this diagram for nitrogen, and this is maybe a good quick review of MO theory. So remember nitrogen looks like a 2s2, 2p3, so it looks something like this. And then our diagram for N2 goes something kind of like this. We have this base diagram. You get the base diagrams again for the final. So you'll see in your supplied info, you get a diagram that kind of looks like this. And we're just filling 2, 4, 6, 8, 10 electrons. And what I'm just trying to say is that there's a big energy gap between those two orbitals. So one of the reasons why N2 doesn't conduct electricity, it's not a good conductor like a metal is because this energy has to be supplied to move an electron up to here. If a metal has an electron right here that we then want to move up to here, there's almost no energy associated with moving that electron into that higher energy orbital. And so that's the idea of conductance, is you can move electrons into these high energy orbitals that then moves the electron through the structure of the metal very easily without an energy cost associated with it, where most of your conductors have a gap. They have what we call a band gap. So this slide here is kind of showing you metals, no effective band gap. Semiconductors have a moderate band gap, and then insulators have a huge band gap. So if you think of the gap between the filled versus the unfilled MOs, most of your molecules that are molecular are over here. So these are mainly our molecular compounds. These are our covalent networks. Usually, well, the covalent networks are usually on the semiconductor side. So usually your semiconductors in the middle, your metals, no band gap, and then your molecular compounds, your molecular solids have that larger band gap. Again, I doubt you're going to see anything on the test about band gap, but this is where you get the comparison between materials versus like molecular solids, is materials have these like interesting properties. You can make, like semiconductors out of the properties that are semiconductive. You want to build structures or wires or things out of metals that have a stronger structure, more durability. So it gives you a sense of how you might want to use a substance if you think about some of its properties. Now, metals tend to have different types of shapes. This is just kind of showing you that metals take on a variety of geometry. Sometimes metal atoms just link sphere on sphere, like one sphere after the other in 3 dimensions. Sometimes they have a slightly more sophisticated structure where you have an atom in the middle. And again, you're never going to probably be asked about anything about the geometry or the bonding nature of metals, but there's 3 key different network structures that metals tend to fall into. But metals tend to be crystalline in this regard. They tend to have a very specific repeating pattern of their metal atoms, and it's usually either a head-on fashion, it's usually either we have like 4 atoms, 1 in the middle, or it's just we zigzag. Zigzagging is best. It's like the best way to use space. So this is the best utilization of space on the face-centered cubic. This is the next best, and the primitive cubic is the worst. So in terms of the space utilization, face-centered cubic best uses space. But there's a variety of reasons why metals would adopt one structure compared to the other. But I think the key is seeing that metals tend to have a repeating pattern. Having a repeating pattern is crystalline. So anything with a simple repeating pattern is what we call crystalline. And things that are crystalline appear more brilliant. So this is why most metals have a shiny luster to them, because they have the same geometry. So if you're shining light off a metal, it has all of its atoms in a very similar geometry, so it's going to reflect light to be a bit more bright than a substance that doesn't have a patterned organization of its atoms. So I think the only conclusion here that I hope you draw is that metals are crystalline. because they have some type of pattern about them in terms of their geometry. This slide, I just wanted to kind of show that metals do have a variety of melting point trends that if you look at, we looked at top to bottom alkali, we remember that the melting point tends to decrease, but there's a lot of weird properties. Like if you go in the middle of the transition metal series, this would be, if you're going from potassium to calcium, this would be like the manganese, chromium, manganese, iron, kind of right in the middle of the transition metal group. The middle of the transition metal group end up having the greatest ease of moving their valence electrons around. They tend to have the highest melting points. So we're looking at melting points. So we get the middle of the transition metal block has the highest melting points. The tungsten we mentioned earlier is right here. Really high melting point. Tungsten, rhenium, osmium, those would be really high melting points. And then when you get back to like zinc, cadmium, and mercury, we get back to like lower melting points. So this would be zinc, cadmium, and then mercury. We also then get back to the decreasing melting point. So I don't necessarily want you to pick up the trends here. I doubt you'll be asked on the trends of melting points, but I just want you to see that you get a variety of properties of melting points across the transition metal series. For some reason, it's best in the middle of the transition metal series. We're not going to offer an explanation as to why, but just like kind of noting that, okay, we get a variety of melting points, highest in the middle. For some reason, bigger in terms of tungsten was better than smaller in the case of chromium, but then bigger in the case of mercury weakened its melting point. So a lot of interesting melting point trends that you see here, a wide variety of melting point trends from left to right. This is showing you another comparison of crystalline, in this case of an iron sulfide mineral called pyrite, which has a crystalline network, so it's shinier. And then we have something called obsidian here, another mineral that is amorphous. Now, what is the difference between those two words? Well, crystalline means that we have a repeating pattern in the iron sulfide, and then this structure here has all these atoms just intermixed randomly. So this is just a random mix of those elements with no pattern. And then this has a repeating pattern. So crystals just have some sort of repeating nature about the solid that repeats itself in 3 dimensions. Now, one of the things with repeating patterns is they're not always perfect. Like if you've ever bought a diamond, or in the future you hope to buy a diamond, you get like a classification chart on its color, its luster, the 3 C's or whatever of the cut, the clarity, and the color. Now, as you get imperfections, every now and then a diamond might have a sulfur where there's supposed to be a carbon. That's going to give it a yellowish color to it. And so you're going to get more color into a diamond the more impurities there are. So you can always have impurities in a substance. So sometimes if something's not totally shiny, it's probably because it has some impurities. It's not a perfect repeating pattern, but maybe 99% of the time it is. Something that appears duller, so the obsidian, doesn't appear as bright, doesn't reflect light as intensely because it has different atoms that aren't in the exact same spot. So it doesn't have the same pattern, so it's not reflecting light in the same way across its structure. So crystalline, ordered repeating pattern, but not perfect. Nothing's ever 100% perfect. And then amorphous, they lack that order, so they are just kind of like a frozen liquid. I think we'll wrap up there for the day. We just have a few more slides to go. So we'll wrap up. Today's keyword is Newton. One more lecture to go. Yeah, so I'll see you guys here on Wednesday. Have a good day.